Hi, my name is Hubert Zając. I'm a postdoc in human-centered AI at the University of Copenhagen. I would like to talk to you today about our qualitative systematic review titled Clinician-Facing AI in the Wild, taking stock of the socio-technical challenges and opportunities for HCI. This paper investigates pretty much everything that can contribute to a success or a failure of an AI-based system in clinical practice. And we wanted to investigate it because we see a great number of exceptional models that perform amazingly well in lab evaluations and are failing or not meeting the expectations in clinical practice. This dichotomy was partially captured by Koyera when he described the last mile problem. That is a problem of transitioning an AI based system from a lab to clinical practice. For example, Bede and colleagues conducted a prospective study of a very high performing model detecting diabetic retinopathy. They deployed a system in a few clinics in Thailand to assess images and refer patients with AI detected retinopathy for further consultations. And the results were less than what they probably hoped for. From treating hundreds of patients every day, the clinics managed to treat only dozens. The participating nurses advised patients not to take part in the study, and the system failed for about 20% of the patients. So that was a great paper that perfectly portrayed the challenges encountered during the last mile. So the natural question for us who worked on a project that aimed to develop and deploy an AI-based system was, why is it so difficult to realize in clinical practice? We decided to conduct a qualitative systematic review to find and learn from papers like the one by Bede and colleagues about the challenges of designing, developing, and deploying systems in clinical practice. And it's worth clarifying that I'm going to jointly refer to these steps as the innovation process throughout this presentation. So we found 9,672 potentially relevant publications in computer science and other healthcare outlets. Within those, we wanted to find publications that described a machine learning based system that affected medical outcomes. Papers that investigated implications for clinical practice included some version of a system, described subjective and qualitative data, and involved medical professionals. Out of these, 25 met our eligibility criteria. And in this presentation, I will briefly highlight the main contributions divided into three takeaway points. I will start with the overview of the technologies and the innovation processes described. First, we provided an overview of the technical aspects of machine learning based systems, like data type, type of machine learning algorithm, integration methods, and development approach. We also highlighted their consequences for the innovation processes. For example, how the type of machine learning algorithm affects the opportunity for collaboration. Second, we described the different roles that machine learning based systems can take in clinical settings. For example, decision support, prioritization, or automation. Namely, the intended uses of AI in clinical practice and how they affect the expectations of performance. Finally, we conceptualized main activities of medical machine learning innovation processes. Based on the processes reported in the reviewed studies, we conceptualized 10 main activities. Importantly, these activities were not uniformly conducted and they involved various stakeholders and various techniques, which highlighted the complexity of clinical AI innovation and the lack of commonly accepted processes. The second main contribution from our systematic review are the sociotechnical interdependencies that affect the realization of AI in clinical practice. In total, we conceptualized 5 challenges. Particularly, these challenges were not of single origin, rather, they stemmed from the interdependencies between the social aspects of the practice and the technical aspects of the implemented systems. And I will go through some of the examples from these interdependencies. And we can start with the connection between the system and integration and the workflow and organization. This sociotechnical dependency suggests that while the underlying machine learning model and the embedding system may prove to have promising performance in lab settings, success in clinical practice hinges on the quality of integration, interoperability with other IT systems, and access to good quality data when the machine learning based systems are deployed. Which means that the use of AI based systems may result in additional steps in clinical workflows, like manual data entry or printing AI output. It can also result in spending additional time on waiting for AI predictions that were for some reason not available at the decision point, or filtering through a sea of false positive predictions due to poor data integration. Also, AI may cause overutilization of resources. For example, to reduce the risk for the patients, an AI-based system may issue way more referrals than a clinician would, as in the paper by Bede and colleagues. Or, like in this example, medical professionals may be given new tasks that were unaccounted for when designing the integration of the system. In the paper by Sand and colleagues, we learned that the developed system was meant to be used by nurses. However, in order for the information provided by the AI to be useful, it had to be disseminated among other medical professionals in the department. And this additional task for the nurses effectively took their time away from caring for the patients. The next challenge is related to the user interface of an AI-based system and its effect on the user and the use of the system. And here we observe that the sociotechnical challenges emerge from the interplay between the machine learning-infused user interface and the clinical end user. For example, we noted reduced trust due to poor and missing explanations, which prevented the end users from drawing their own conclusions and assessing the validity of AI predictions. We also found shifted accountability among medical professionals when only some of the practitioners were using AI. We also described the risk of confirmation bias when interacting with AI output, like in this example by Kai and colleagues, whose participants became wary of too much interaction with AI. The final interdependency I will explore in greater depth is the relationship between the user and their use of the system and the effect on their needs towards the machine learning-based system as a whole. This dependency suggests that an effective adoption of machine learning-based medical systems may be rooted in human and social dimensions related to the clinical end user rather than in the technical aspects of the systems. We discovered that when providers had little knowledge about machine learning and predictive modeling, they found themselves unable to assess and verify the predictions and their credibility. Also, insufficient training and explanations affected the way that medical professionals use the system. And finally, functionality expectations for the systems varied depending on the clinical position of the end user. For example, Bard and colleagues reported on completely different needs of two end user groups, nurses and doctors. Nurses wanted minimal, actionable information and tended to prefer simpler, static explanations, while physicians preferred more dynamic explanations that would help them engage with the data and draw their own conclusions. Finally, the last takeaway are the recommendations for HCI researchers and practitioners on how to navigate and contribute to realizing clinical AI. First, I would like to highlight that AI-based systems are not conventional IT systems. They require a lot of preparatory data work, they are subject to stricter regulations, they are more difficult to design, and they impose new ways of interaction. And what's more important, they are created through situated, messy, and collaborative processes between practitioners from 3 different domains. And the collaboration between these domains is very challenging due to the lack of shared workflows, lack of shared practices, concepts, and the fact that we come from very different traditions, have very different goals, and have very different metrics when working on AI-based systems. So when we look at the traditional development focus across the domains, we can simplify it to the following. In healthcare research, traditionally, the use of AI-based systems would be considered medical interventions, and their innovation would follow a sequential process. A process that depends on systematic approach, values randomized clinical trials, and isolates the intervention from any external confounding factors during evaluation. And from the point of view of AI engineers and HCI designers, this is a bit problematic because AI is highly dependent on those very local factors. And when we look into machine learning development, we will see that the majority of the work is conducted on data. It's about data collection, data cleaning, data labeling. And this again is often done in the safety of labs and isolated from practice, which for many reasons is not ideal. But then when we have the data, the model is trained, the data is improved until we reach a moment when we are ready and allowed by the regulations to try the model out in the wild. And while this work is usually iterative, often the realization of constraints, wrong assumptions during data creation, or the sociotechnical challenges happens only after the deployment into the wild, which again happens quite late. And finally, in terms of HCI, the preferred development lifecycle assumes quick, short, iterative cycles of developing particular features, especially engaging real-world users in local contexts is a core principle of design work in HCI, and this clashes with the other paradigms and complicates collaboration. These clashes were well captured by Blandford and colleagues, who write that until there is much greater mutual understanding and mutual valuing of the complementary research tradition than exists at present, people will risk disappointment and rejection in trying to bridge the divide. And this goal perfectly aligns with the recommendations included in our paper. Namely, first, to realize sociotechnical dependencies and capabilities of AI-based systems in practice, we recommend that AI-based systems are co-constructed as part of real-world clinical practices through near-life and real-world experimentation. Second, these real-world engagements should preferably inform all the stages of clinical AI innovation. That is, we recommend that as much as possible, we combine the design, development, and evaluation work, as rather than solely medical or technical endeavors, innovation of clinical AI should be approached as innovation of socio-technical systems. This in-practice activities should focus on enhanced mutual learning and deeper collaboration between medical professionals, machine learning engineers, and HCI practitioners when innovating AI-based systems, as knowledge from all these three areas is relevant throughout the innovation process. And understanding domain-related limitations may result in fewer misconceptions and misunderstandings when deployed in practice. Finally, we suggest that this work should be guided by the intended clinical use from the earliest moments, like data creation, to result in clinically useful systems in practice. And again, here are all the 4 recommendations altogether. And that concludes our presentation. Thank you so much for listening in, and reach out to us if you want to know more or have any comments.